already finished lecture 1 to 5 about diffusion in solid materials. And I believe you already know what is the kinetics and steady flow process. And I believe you also can use the entropy production rate per volume to describe each kinetics process. And regarding to the diffusion in solid materials, first thing you need to identify how many driving forces exist in your material systems, right? And as long as you know, and you can, based on the driving force, you can get the flux, and based on flux, you can formulate the diffusion equation and get the corresponding solutions in macro scale to describe the concentration profile of diffusing atom in macro scale. And we also tell you how to we also further to tell you how the atoms diffuse through crystals in micro scale based on different atomic diffusion mechanisms in metals, and also we address some cases in ionic solid materials. And additionally, we also highlight the diffusion behavior in crystal imperfection size, including the grand boundary diffusion, dislocation, and surface diffusion. So now we are going to move to part 2, including the lecture 6 and 7. It will be talking about the other kinetics process, which is chemical reactions. In lecture 6, we are going to talk about the homogeneous chemical reactions, which means the reactants and products. There's only one phase of reactants and products involved in these chemical reactions. We call homogeneous chemical reactions. And if the phases were more than 2 or more, is more than 2 phases, then the chemical reaction would belongs to heterogeneous chemical reaction. So we are going to talk about the homo and heterogeneous chemical reaction in following part. And in homogeneous chemical reactions, we are going to give you an overview about what's the homogeneous chemical reactions, how to classify them, and also highlight the one we talk about in kinetics will focus on the bench type reactions, and also show you how we can analyze or formulate the rate equation for our interesting unknown chemical reactions. And for heterogeneous chemical reaction 1, we are going to show you how to estimate the reaction rate for fluid, solid, fluid, and even fluid particle cases. So let's move to the lecture 6 here. So as you know, in the lecture 6, we are going to talk about the homogeneous chemical reaction. So in these lectures, we are going to give you an overview about chemical reactions. So how to classify the chemical reactions, and the importance of chemical reactions here would be the rate equation. So I'm going to give you an example. So we use the hydrogen reactor with oxygen, then we can get water as an example. This will be chemical reactions, right? And some people also use the reactant A react with B, then we can generate product C and D. So under these chemical reactions, so we can know the consumption rate of reactant A expressed like the rate constant K times the concentration of reactant A and B. And also don't forget the A and B here is correlated with the reaction order. We also call it as a reaction order. So the most important part in here, because chemical reaction also one kind of kinetics process, and here we very care about how to describe the reaction. Chemical reaction is fast or slow. So the rate equation can be an indicator to describe how fast or how slow this chemical reaction is. And this rate equation also will be dependent with the concentration of reactants. We call the concentration dependence, and also will be depending on the rate constant, and inside this rate constant you can observe the temperature dependence and also have energy barrier from in between, from left-handed side to right-handed side, the energy barrier we talk about. So the rate equation is quite important. In order to complete this rate equation, you need to know the rate constant and also the concentration dependency of the reactants. Okay, so let's we are going to give you further information in first part, and the second part we are going to show you how to analyze the reaction data for bench type homogeneous reactions in your interesting chemical equations. How we can design, how we can get the reaction order, this reaction order and temperature dependency part from experiments data, how to analyze. So we are going to introduce several different analyze methods to show you how to reconstruct this rate equation for your unknown or your interesting chemical equation. Okay, so let's move to the first part, overview of chemical reaction. Okay, so what is chemical reaction? So chemical reaction for sure have an energy barrier. So based on the definition, chemical reaction means we have the formation of products as a result of interaction of reactants, can be collision of reactant molecules or self-transformation or decomposition of your reactants. So if we try to use we will draw the free energy as a function for reaction coordinate, then the chemical equation we deal with is reactant A react with reactant B and generate product C and D. Then you can observe we have 3 stages. First one is we have reactants, and also we have intermediate stage, and also we have product stage. So based on this, this chemical reaction have energy barrier. Delta EACT is also we call the energy barrier. Okay, and here you also can see this chemical reaction with the product will be C and D. And based on energy point of view, we find the stage 3, the free energy of the product actually is lower than that in the reactant side, stage 1. So based on thermodynamics, you know these directions is correct, right? Because these chemical reactions for sure will lead to right-handed side, because this will decrease the total free energy of the system. So the driving force is for sure will be proportional to delta G. And in this case, if we we did not apply the other driving force, there's only thermal energy exists in our system, then we can observe the energy barrier here. So when you try to increase the energy of increase the temperature, then that will allow more reactants have sufficient energy to overcome this energy barrier. So this is this one regarding to the energy barrier. So here, following this, we know thermodynamics just tell you this reaction is the direction for this reaction is go to right-handed side, but thermodynamics didn't tell you how fast this chemical reaction is, but kinetics tell you, right? Based on this equation, the flux equals to minus diffusivity concentration gradient, and also can be written as concentration, mobility, and driving force. And driving force is a minus Gibbs free energy, the gradient of Gibbs free energy. So here you know, if we have a larger delta G, then we will have more flux, higher flux, then that will lead the chemical reaction more faster. So the delta G also will affect the reaction rate. And also the activation energy, as I mentioned before, if you have a lower energy barrier, that also will allow more reactants to generate product. So that also will increase the reaction rate. So both activation energy and delta G will affect the reaction rate here. And then we try to next we need to identify a term we call a spontaneous chemical reaction. So what is a spontaneous chemical reaction? It just tells you that occur under a given set of conditions without intervention and proceed to completion without any external driving force. So this reaction all the way to the right-handed side, we don't need to apply a external driving force. For example, like a salt dissolved in water, ice melting, or iron roasting is all are spontaneous reactions. So because these reactions will reduce the total free energy of the system and accompany with an increase of system entropy. So regarding to these chemical reactions, so you also can, the rate equation will be what we are care about in kinetics process, right? So the rate equation can be expressed like the consumption rate of reactant A times the equals to the rate constant and concentration dependence. Inside the rate constant, we have an energy barrier of these chemical reactions and also the temperature term. And also the concentration dependency part, what we have is we have the concentration of reactants and also the corresponding reaction orders here. So reaction kinetics will depending on how many reactant molecular overcome the energy barrier. So the concentration of reactants and fraction of energetic reactants matters, means these two will affect the consumption rate of reactant A or consumption rate of reactant B or the generation rate of product C or D. So the rate equation, some people use the consumption of reactant A, some people will use the generation rate of product C to express this rate equation. All are fine, all are okay. You can use different description to describe how fast these reactions is, okay? And this temperature-dependent rate constant actually just the idea you learned before, right? The vertical is the number of reactant molecules, and the horizontal axis is the energy of these reactant molecules. When we have a lower temperature at T1, and you can observe just a small portion of reactant molecule can overcome this energy barrier. But when you try to increase the temperature to T2, you can observe the more reactant atoms or molecules can overcome this energy barrier, and it will obey these distributions. The probability or proportion to exponential minus activation energy divided by KT. So now you have some idea about the chemical reactions, right? And also you know what is the rate equations. So next I'm going to ask you would be what factors will affect the output of your interesting chemical reactions. So will be the performance of chemical equation or performance of chemical reactions will be affected by the input, means what kind of reactants you use, what kind of chemical reactions you choose, or chemical equation you choose, and the contacting pattern between the reactants will significantly affect the performance of these chemical equations or the performance of this output. Okay, so the kinetics actually it means what type or what kinds of chemical reaction you choose. Okay, so the other concept will be kinetics, you know, and the other concept will be what is the stoichiometry equation. So we take this A react with B generate product C and D as an example. If it is a stoichiometry equation, then the rate equation can express like this, and this is consumption rate of reactant A can be expressed like equals to rate constant times concentration of reactant A to A, the same with the coefficient here, and times the concentration of reactant B, and the older reaction order will be the same with stoichiometry. I mean the coefficient, the mole coefficient here will be the identical one. Under this situation, we will say this chemical equation belongs to stoichiometry equation. Okay. And besides the kinetics part, the contacting pattern also affects a lot. What's the contacting pattern? It means how the reactants react each other. So this we call the contacting patterns. So that will be depending on the design of reactors. Okay, so we have three different contacting patterns of reactions. So as I mentioned before, contacting pattern actually is how the reactants are mixed and react with each other, and that will depending on how you design your reactors. So what we have here is we have bench type, plug flow, and mixed flow. So what's the bench type means? We put all the reactants in the beaker, and we put the stir bar on the bottom, and to allow this reactant can mix well. So in this bench type, inside this beaker or inside this bench type conditions, we have a uniform composition everywhere in these reactors. But of course, the composition changes with time because we put the reactants in the beginner, and the reactants or the concentration or content of reactants will decrease, and the product will increase. But so this is the means. So this is why we say the composition changes with time. Composition means the compound of reactants will decrease, and the compound of the product will increase. Okay, but no matter what, but the concentration, the composition everywhere in the reactors are the same. So here we say, the composition at any locations inside this beaker or these reactors remain constant, and also but the concentration of reactants or the product will change with time. So this means the uniform composition everywhere in the reactor, but the composition changes with time. And the second one we call it is a plug flow. Plug flow means that we have a tube here, we put the reactants inside here, and these reactants will flow and react in the meantime, and probably from this end we will get some products. So in this plug flow reactors, we find that the concentration are different at any locations, and also the composition will change with time. Okay, so this flow passed through the reactors without mixing, so the concentration is not uniform everywhere. Okay, and the third one actually we call a mixed flow case. They also have a stir bar here, a mixer here, so to make sure the concentration everywhere are the same. And also they put the reactants is a little bit with that in the bench type. In the bench type we will put the reactants in the beginning, but here we always refill our reactants to maintain the concentration of reactants are the same. So under this situation, that will lead you have a uniform mixer, so the same composition everywhere, and also within the reactants, within the reactor and at the exit. But interestingly, the concentration of reactants or product will remain constant because we refill the reactants. So based on these three different types of contacting patterns, my question would be, in your opinion, which one would be the kinetics would talk about what type of contacting patterns? Which one you think the kinetics process will be more interesting in that? Is this one? No. The bench type will be the one contacting pattern we always talk about in kinetics. Why? Because in bench type, the concentration of reactants or product change with time. As I mentioned, kinetics talk about as a function of time, right? But in this case, the concentration does not change with time, so kinetics is not interested in this one. And this one is change with time, yes, and this one also change with time, right? But this one, the concentration distribution is not uniform, so that will make the reactions more complicated. So the batch type is the one we always talk about in chemical reaction part in kinetics. kinetics. Okay, today we end it here.